Hi, friends. It's our last exciting lesson for this week, our post-Memorial Day week after. Hope you guys had a great weekend. It's going to be so nice out. I can't wait. Okay, so we've got relationship 1. We're going to talk about chord relationships. We're moving away from all the angles in the circle to talking about the actual chords. So things like chords and tangents and secants and all sorts of those fun things. We're going to actually be working on the segments and circles now. Whereas the last couple of weeks we were doing the angles. The first relationship is parallel chords. Woo! If two chords are parallel in the circle, for example, in this picture here, they intercept arcs that are going to be congruent. So in this case, since these two chords are parallel to each other, the arcs that are in between them, like AC and BD, those two arcs are going to have a measure. Very exciting. Okay, so let's look at this first example here. So they're telling us, which is really hard to see, that this angle is 35 degrees. Now that's an inscribed angle. Remember, if they're inscribed, they're half of what the arc is. So in other words, the arc has to be double this angle. So this guy out here is now 70. And since these guys are marked parallel, its friend over here is 70. And look, this is a fun diameter. It looks like it's going through the center. So that means this arc up here is 180. If I have 140, that means this arc over here is 40. I just found all the arcs of that circle without even doing anything. Let's see what they want us to find. The arc CE, I already found it. It's 70. Arc BD, already found it. It's 70. And E to D I found was 40. Because of this diameter, it had to add up to 180. That was so fun. Let's do another one, friends. Okay, so we have this arc up here being 60. These chords are parallel. That guy's 80. Guess who's 82? The angle, the arc on the other side. Now I have 160 plus 60. 160 plus 60 is what? 220. So do I have 360? Wait, 160 and 60 is 220, right? So do I have 140 degrees left for this arc down here? I think so. That was super fun. Parallel chords intercept congruent arcs. That's our first relationship. Next relationship. If there are congruent chords, then they have congruent arcs. Look at this. AB, the chord, and CD, the chord. So if segment AB is congruent to CD, then guess what? Their arcs is congruent to arc CD. If the chords are congruent, their arcs are congruent. Okay, so in this picture, I see these two chords are marked congruent. So if this is 106 for the arc, so is this 106 for the arc. So now I can just add up all those arcs in the circle, subtract them from 360, and I end up getting 115 over here for that nice arc that I was looking for. Super easy. Okay, it says solve for x. So see how this and this are marked. Well, that means this arc here is congruent to this arc here. And since those arcs are congruent, that means those chords that intercept them have to be congruent. So if these pieces are 2 and this guy is 10, then this piece also has to be 10 because they intercept those congruent arcs. Same idea here. Look, all of these chords are 8.5. That means all of these arcs are all x. This one was already marked x. So basically I have 3x plus 108 has to equal 360. Or 3x has to equal 252. Or in the end, that guy has to be 84 for those 3 arcs. Each one's 84 degrees. That was super fun. That's relationship 2. Relationship 3 says, Chords equidistant from the center of a circle. In a circle, congruent chords are equidistant from the center. That does make sense. So if these two chords are congruent, then the distance from the center out to them also has to be congruent. Okay, so let's look over here at this example. They're saying this guy from the center to this guy is the same distance. That means these two chords have to be equal in length. Well, if I know part of it is 6.5, this guy's also 6.5. So then I can just simply add 6.5 and 6.5, and I've got 13 for my answer on there. That was pretty easy, wasn't it? Okay, so now let's check out this next one. This is a little bit trickier. Chord and a diameter. So it says, in a circle, a radius that bisects a chord is perpendicular to the chord. So here's a radius or a diameter, because a diameter is just a fancy extension of the radius. It means that it's making a perpendicular to that. It also bisects it there. That's kind of fascinating. Okay, so let's look at this example down here. Basically, the diameter acts as the perpendicular bisector to that chord. So this says solve for x. All right, well, this is a little trickier. I know this guy's 3. Because it's bisecting there, this also is 3. I don't know if that really helped us or not, but I'm going to observe that this x is actually the radius. And if it's a radius, it's going to be the same no matter where it is in the circle. So I'm just going to simply swing here. And I can use my good friend a squared plus b squared equals c squared, or my Pythagorean theorem. However, since it's the almost June and you are in geometry honors, you know that if it's 3 and 4, that other guy should be 5, because this is a 3, 4, 5 Pythagorean triple. So our answer will actually be 5. If you don't believe me, you can do 3 squared plus 4 squared equals c squared. 9 and 16 add up to 25. So c squared is 25, or c is 5 in that case. If you know your triples, it's super helpful. Let's look over here. Now this guy is 4, and the whole thing is 10. So this guy's 5, and this guy's 5. Does that mean this is 3? No, 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 because that's the hypotenuse. It can't be shorter than the side. That's 5. C squared equals c squared. And I'm looking for my hypotenuse. So what is that on there? 4, I wrote over it and I can't see it. 4 squared plus 5 squared equals c squared. 16 and 25 is c squared. C squared ends up being, 41. It says leave it in simplest radical form. I can't break down square root of 41, so square root of 41 is my answer. That was super fun, folks. And it's super nice out. So I'm going to get inside my pool right now, and you can find me there later. Bye.